Now we are moving to analysis of two-dimensional ideal flows. We know we have real fluid flows with the effects of viscosity and ideal fluid flows in theory where there is no viscosity and compressibility effects in ideal fluid flows. However, we know these ideal fluid flows are not possible in the reality. The ideal flow theory may also be extended to situations in which fluid viscosity is very small and velocities are high. Since they correspond to very high values of Reynolds number at flow are independent of viscosity. The study of ideal flow provides mathematical expressions for streamlines in elementary or basic flow patterns. Let us try to look at linear motion in 2D frame. For that, we need to have limiting rotational flow. Therefore, let us try to understand rotational and irrotational flows. Please refer the top figure. We can have two types of motions. First, the translation, that is the linear motion, and the second, or the B, is rotation, that is the angular motion. These two types of motions may exist independently or simultaneously. Now let us look at another stage of motion, that is the deformation. The deformation also could be linear or angular as shown in the lower figure. Now let us try to mathematically express the motion and the deformation. Refer the diagram. Point A moved to A prime at a dt time step. However, two legs in horizontal, that is AB, and vertical AA, rotated at A prime in alpha and beta angles as shown. The AB distance is dx and AA distance is dy. For the rotation, we can define the angular velocity. We know angular velocity is angle or rate of angle. Now, here we have two angles of rotations, that is alpha and beta, which we assume they are not equal. Therefore, let us take the average angle, that is alpha plus beta divided by 2. Therefore, the omega angular velocity is alpha plus beta divided by 2 divided by dt. Let us use our geometrical knowledge and find the angular velocity. With a bit of mathematics, we can find out that the angular velocity omega is half Vy over x minus Vx over y. Please note the direction of the angular velocity is in z direction since the rotation takes place in xy plane. Let us call this Vy over x minus Vx over y to be the vorticity. Therefore, we know vorticity is 2 times omega. We know if the flow is irrotational, then there is no angular velocity. Thus, omega is 0 and the vorticity is 0. Therefore, Dabba v y over dabba x minus dabba v x over dabba y is equal to 0. In this module, we are going to work only with the irrotational flows. Let us define two-dimensional velocities using velocity potential. If we consider the velocity potential to be pi, we define Vx, the velocity component in horizontal direction, to be dabba pi over dabba x, whereas Vy, the vertical velocity component, to be dabba pi over dabba y. Therefore, velocity potential pi is a function of x and y. When we apply the velocity potential in two-dimensional continuity equation, that is dabba Vx over dabba x plus dabba Vy over dabba y is equal to 0, then we can obtain the following relationship, that is dabba squared pi divided by dabba x squared plus dabba squared pi divided by dabba y squared is equal to 0. Now this should be familiar to you. This has the Laplace equation form. Similarly, let us define the stream function. Let us call the stream function to be psi. So we define Vx to be dabba psi over dabba y, Vy to be minus dabba psi over dabba x. When we apply this stream function relationship to irrotational flow relationship, we can see that it is again satisfying the Laplace relationship, that is dabba squared psi over dabba x squared plus dabba squared psi over dabba y squared is equal to 0. Now, let us look at the properties of stream function. Please recall your memories on stream function and its properties from our previous sections. In addition to that, we can mathematically present that the flow rate in between two stream lines are given by small q is equal to psi2 minus psi1, that is the subtraction of the stream functions. Another property of stream lines is that they are perpendicular to equipotential lines. They produce curvilinear squares. If we consider the total derivatives of streamlines and equipotential line, we can prove that they are intersecting each other perpendicularly. The multiplication of the inclination of a streamline and equipotential line gives us -1. That means mathematically proved that they are perpendicular to each other. Now this diagram shows a flow net. So we can draw these streamlines and the equipotential lines to the flow situations, and we can use the this particular property, that is the subtraction of stream functions, to calculate the total flow rate in the system. That concludes this session.